All right, let's talk about something every developer needs in their toolkit, the solid principles. We're going to break down exactly what they are, and more importantly, how they can be your absolute best defense against that messy, tangled code we all hate.
So, you ever inherit a project and it feels like you're wrestling a monster? I mean, you know the one, right? It's this fragile, tangled mess where you change one tiny thing over here and a whole bunch of stuff breaks over there. It is a total nightmare, and honestly, we've all been there.
And you have to ask yourself, how does good code go so bad? How does a project that starts out all clean and promising just decay into that beast? Well, a lot of the time, it's because the foundation just wasn't there from the start. And that is exactly the problem Solid is here to solve.
Okay, so let's meet our monster taming toolkit. Solid isn't just one big idea. It's a powerful set of 5 distinct design principles. Think of them as your guide to building software that's better, more robust, and just easier to live with.
Now, SOLID is actually an acronym for 5 principles, made famous by the one and only Robert C. Martin, aka Uncle Bob. And their whole purpose, really, is to help us hit 2 huge goals. First, high cohesion, which just means keeping code that does one thing all together in one place. And second, low coupling. That's all about making sure that changing one part of your system doesn't cause a domino effect that breaks everything else. If you can nail these 2 things, your code is immediately going to be so much easier to understand and test.
All right, first up, let's talk about the S. This stands for the single responsibility principle. And you know, a lot of people say this is the most important one of the bunch because it really sets the stage for all the others.
The idea here is actually super simple. A class should have one and only one reason to change. Basically, it should do one job. A really great rule of thumb is this. If you find yourself describing what your class does using the word and, like, oh, it calculates the total and it prints the invoice, then you've probably given it too many jobs. It's a dead giveaway.
Okay, check this out. This is a perfect example. On the before side, you've got this one Factura class that's doing everything. It's handling the business logic, it's printing, and it's saving to the database. That's a mess, because anytime you need to change how printing works, you risk breaking the calculation logic. But look at the after side. We've split that logic into 3 separate focused classes. Now each one has just one single reason to change. The whole system is just safer and way easier to manage.
All right, next up, we're going to tackle O and L together. That's the open-close principle and the Liskov substitution principle. The reason we're looking at them together is that they're both all about building these flexible class structures that you can add to without, breaking what's already there.
So, the open/closed principle is a real classic. The famous line is, open for extension, but closed for modification. So what on earth does that actually mean? It's simple, really. It just means you should be able to add new features or new functionality without having to go back and change code that already exists and is already working.
Think about it like this. Let's say you have a function that calculates the total area of a bunch of shapes. Right now, it only knows how to handle rectangles. What happens when your boss says, hey, we need to add triangles? Well, you have to go in and crack open that function and add new logic. And then what about circles? You have to change it again. Every new shape means changing existing code, and that's just asking for bugs. This is a total violation of the principle. It's not closed for modification at all.
And that leads us perfectly into the Liskov substitution principle, or LSP. I know, it's a fancy name, but the idea behind it is pretty straightforward. It just says that you should be able to swap in a child class for its parent class, and the program should not blow up or do something weird. The classic way to put it is, if it looks like a duck and quacks like a duck, you should be able to treat it like a duck without any nasty surprises.
Now, this is the textbook example of where LSP gets violated.
In geometry class, sure, a square is a rectangle. But in code, it gets tricky. Just look at this. We create a square, but we treat it like a rectangle. We set its width to 5 and its height to 4. So logically, we expect the area to be 20, right? Wrong. Because with a square, when you set the height, it also changes the width. So the area is actually 16. The assertion fails, our program breaks, and we're left scratching our heads. The square just isn't a good substitute for a rectangle here.
Okay, we're on the home stretch. Let's wrap this up with the last 2 principles, I and D. These are all about designing clean interfaces and getting smart about how different parts of our code depend on each other.
So the I is for the interface segregation principle. This one is all about fighting against what we call fat interfaces.
You know, these huge, bloated interfaces that have a million methods. The principle says that you shouldn't force a class to implement a bunch of methods that it doesn't even use. It's just clutter, and it leads to all this weird code with empty methods, or worse, methods that just throw an exception. Here's a great example. On the before side, we've got this one giant iPayment processor interface. So our poor credit card payment class is forced to have methods for processing PayPal and Bitcoin, which it can't do. It makes no sense. The solution? Break it up. On the after side, we have smaller, specific interfaces. Our credit card payment class now only implements the credit card interface. It's so much cleaner and just makes way more sense. And last but not least, we have D for the dependency inversion principle. This one sounds a little academic, but the idea is crucial. It says that your high-level code, the important business logic, shouldn't depend directly on your low-level code, like the nitty-gritty details of talking to a database. Instead, both of them should depend on an abstraction, like an interface.
So here's how we fix it. We literally invert the dependency. Instead of our important logic depending on the database details, we stick an abstract interface right in the middle. Now, the high-level logic depends on the interface, and the low-level database code also depends on the interface. This little flip is unbelievably powerful. It means we can easily swap out our database for, say, an API service, or even a fake object for testing, and we don't have to change a single line of our important business logic. It's a game changer.
Okay, so we've walked through all 5 principles. They sound pretty great in a perfect world, right? But the real question is, how do they actually hold up in the messy, chaotic reality of our day-to-day jobs? There's a really great piece of wisdom that floats around the developer community that just hits the nail on the head. Solid principles are principles, not laws. And that's so true. They're incredibly powerful guidelines for sure, but in the real world, with deadlines and trade-offs, you have to apply them with a bit of common sense and judgment. And this really shows that balancing act. On the one hand, our goal is clear. We want code that's easy to maintain and test. But on the other hand, there's a trap. If you follow these principles too rigidly, like a dogma, you can end up with something that's way over-engineered and even more complex than what you started with. Remember, the point is to build great software that works, not to create some kind of perfectly pure architectural masterpiece.
So that leaves us with maybe the most important question of all. It's one thing to know the rules, but real mastery, that comes from knowing when it's okay to break them. So, when is breaking a solid principle actually the right decision? The answer is, it depends. Context is everything. Because at the end of the day, the goal isn't just to be solid, it's to ship great software.